Here we are going to look at the Monty Hall problem. You are on a game show and you are asked to choose between 3 doors. Behind one door is a prize, and behind the other 2 are goats. The host Monty Hall would then come and open one of the doors which has not been selected by you and give you an opportunity to either stay with your original door or switch to the other unopened door. Monty Hall, the host, knows exactly what is behind the door, and he will always choose the door which does not have the prize behind it. Now, when considering whether to stick or switch, you would think that this doesn't make any difference, right? Either the prize is or it isn't behind the door, and therefore why would switching make a difference? So normally, if we are calculating the probability for finding the prize, it is basically a 1 in 3 chance. Now in reverse, that means that there are 2 in 3 chances here to get no prize. The Monty Hall problem is a well-known problem, mainly because there was some disagreement at the time over what the right answer to this problem should be. Even some really smart people didn't agree on what the right answer should be, and part of the disagreement is that they probably were considering slightly different variations of the problem, because in all probability problems, the assumptions that you are working with are very important. The reason for this is that you could actually be solving a different problem. So for a minute, let us consider there being more than 3 doors. Monty Hall could have 10 doors instead of 3. There is still just 1 car and all of the other doors are filled with goats. Let's say you pick the first door. It is likely your door contains a goat, as you have a 1 in 10 chance of winning the car. You do, however, have a 9 in 10 chance of receiving a goat. Monty will now open 8 doors, knowing that each contains a goat. So now should you switch or should you stay? The prize was not behind any of the 8 doors that were previously opened, so it is very likely that it will be behind the leftover door which was not opened. So you should definitely switch. If you switch, you have a 9 in 10 chance of winning the car versus a 1 in 10 chance if you don't. Now let's return to the original problem. The same reasoning from the 10 door problem applies here. Your door is more likely to contain a goat than a car. The other doors are more likely to contain a goat and a car than 2 goats. So even after Monty opens the door with the goat, it is still more likely than not that one of these doors contains a car, but only the unopened one can. So switch it. Switching gives you a 2 in 3 chance of winning, whereas you will have a 1 in 3 chance if you don't switch.